In this video, we're going to take a look at the first problem from the second order systems with step inputs problem solving session. And the first thing that I'm going to do is I'm going to solve this using the node voltage method. So in this problem, we have a series RLC circuit that's connected to a 24 volt supply. And we also have this 1 ohm resistor that's connected across the capacitor C1. At time t0, the switch is going to be suddenly opened, and we are to determine what the voltage or how the potential across this capacitor right here, C1, is going to end up changing as a function of time. Okay, so the first thing that we need to do is we need to derive or develop the differential equation that's going to describe how the potential across the capacitor C1 is going to change after that switch is opened. So after the switch is open, the resistor that was over on this side of the circuit, over on the right-hand side of the capacitor, is no longer present. So the circuit that we're looking at is just a series RLC circuit. Since we're interested in the potential across the capacitor, it would make sense to begin with using the node voltage method to solve for a voltage or a potential. Now, we're going to see later that we could also use the mesh current method to solve for the potential here, but I'm going to start off using the node voltage method. So the first step in the node voltage method is to determine the nodes that we have. And remember that a node is defined as being a junction between two or more elements. So we see right here we have a junction between the ground or the low side of the supply voltage and the capacitor, so that's a node. We have a node right here between the power supply and the resistor. We have a node between the resistor and the inductor, and we also have a node between the inductor and the capacitor. Now, the next thing is that we have to define what is our reference node, so I'm going to select this as being our reference node right here. Now, the good thing about that is that our reference node is connected to this node via a power supply, so we know that this node right here is the same thing as the input voltage Vn, so we don't have to develop a node equation for that node. However, we have two other nodes that we still need to develop equations for. The first one is the output voltage node, which I'm going to call Vout, and the second one is the node that exists between the resistor and the inductor, and I'm going to call that one VA, V sub A. Okay. Now we're going to have to develop our node equations. So I'm going to start with VA, and we're going to use Kirchhoff's current law because that is the basis of the node voltage method. The current law says that all of the current leaving the node must sum to 0. So the current through the resistor plus the current through the inductor must be 0. And now we're going to use our relationships to relate the current to the potentials at the unknown nodes. Alright, so for the resistor, it's the potential difference across the resistor divided by the resistance. The potential difference across the resistor is given as VA minus Vn divided by R1. Now, the current through the inductor is related to the potential across the inductor by an integral relationship. That's 1 over L times the integral of the potential difference across the inductor. Now, the potential difference across the inductor is going to be the voltage at this node minus the voltage at this node, both with respect to ground. So that will end up being VA minus Vout dt plus the initial current through the inductor at time 0, and all of that must equal 0. Now, the next thing that I'm going to do is I'm going to do the node balance for the Vout node. For the Vout node, we know that the current through the inductor plus the current through the capacitor must sum to 0. IL plus IC must equal 0. And now we'll just use our relationships to relate the voltages, the currents to the voltages. Alright, for the inductor, the current through the inductor is related by the integral relationship 1 over L, and now we're using this node as we're assuming that this node is at a higher potential, so that current will go from the Vout node towards the VA node. So our relationship will be Vout minus VA dt plus the initial current through the inductor in that direction plus the current through the capacitor. Now the relationship between the current and the voltage through a capacitor is given by the derivative relationship of C times the derivative of the potential difference across the capacitor, which is V out, minus our reference node, which is assumed to be 0. Okay, now we see that we have two equations that we need to couple together so that we can come up with a single second-order differential equation. Okay, so the way I'm going to begin this is I'm going to look at my V out equation right here, and I see that I have a single term that's related to the voltage at node A. If I can get that voltage isolated by itself, or that term isolated by itself, then I can substitute it back into this equation right here. Alright, so the first thing that I'm going to do is I'm going to multiply everything by L. Yes, the first thing I'm going to do is multiply everything by the constant L so that I can make my life a little bit easier here. So that will give me the integral of V out minus VA dt plus L times IL times 0 multiplied by the inductance times the capacitance times the rate of change of the output voltage across the capacitor must sum to 0. Okay, so the next thing that I'm going to do to get rid of my integral term here is I'm going to take the derivative of this entire expression, my entire equation. So I'm going to take the derivative of the right-hand side and the left-hand side. Of course, the derivative of 0 is still 0. So when I do this, I'm going to get my integrand value. So that's going to give me V out minus VA. This is just a constant term right here, so that term will go to 0 when I take the derivative. And I will have my constant LC multiplied by the second derivative of the output voltage with respect to time. Okay, and from this I can solve directly for VA, and the voltage at node A will be given by this second order equation. Okay, the next thing that I need to do is I need to substitute, I'm going to have to substitute this back into my node A equation. Well, my node A equation, I'm going to make that look a little bit different. And how I'm going to do that is I'm going to take the derivative of this so that I can get rid of this integral term. When I take the derivative of this, what I'm going to wind up with is dVA dt. This is going to be multiplied by 1 over r minus 1 over r times dVn dt plus 1 over L VA minus 1 over L V out equals 0. Okay. Now from that, since I've solved for VA, I can now substitute VA back into this equation right here, and I'll have everything in terms of V out and Vn, which is what we need. But to do that, to substitute this back in, I need to take the derivative of this definition of VA right here. So VA, so the derivative of the node A solution with respect to time is going to give me now a third derivative with respect to time plus a first derivative with respect to time. Okay, so now I'm going to take these terms and substitute them back into this expression right here. Okay, so dVA dt is this entire term right here. So I'm going to take this and substitute it in here. So I'm going to multiply everything by 1 over r. So I will get 1 over, LC over r times the third derivative of the output voltage with respect to time plus 1 over r times the first derivative of the output voltage with respect to time. This dVn term, I'm going to move to the other side of the equation, so I'm not going to worry about that right now because that's my input term. And now I'm going to multiply 1 over L by my definition of VA. So I'm going to substitute this back into here. All right, when I do that, I will wind up with the L's will cancel here, so I will get C times the second derivative of the output voltage with respect to time, plus 1 over L times the output voltage with respect to time. And then I'm left with my third term right here, which is minus 1 over L V out. All of that has to be equal to 1 over R dVn dt. Now from this we see that our zeroth order derivative terms are going to cancel each other out. Right? And in doing so now I can rearrange my equation. I see that I have a third order derivative, a second order derivative, and a first order derivative. So in order to reduce the order of those derivatives, what I can do is I can take I can integrate this entire expression now. I can integrate both sides of the equation. So first of all, let me rearrange this. So I will have LC over R times the third derivative of V out with respect to time, plus C times the second derivative of V out with respect to time, plus 1 over R times the first derivative of V out with respect to time has to be equal to 1 over R dVn dt. Okay, and now I'm going to take I'm going to integrate this entire expression. When I integrate that entire expression, basically what I'm doing is I'm reducing the order of each of the derivative terms. All right, and so when I do that, I will wind up with the following: LC over R times the second derivative of the output voltage with respect to time, plus C times the first derivative of the output voltage across the capacitor with respect to time, plus 1 over R times dV out, times the zeroth order derivative of the output voltage with respect to time is equal to 1 over R times the input voltage. Okay, so now we can do a little bit more rearranging to make this look a little more appealing. So what I'm going to do is multiply everything, both sides of the equation, by the resistor value R1, and that's going to give me LC d squared V out dt squared, the second derivative of the output voltage with respect to time, plus RC times the first derivative, plus, and if I multiply by R, this will just be the output voltage, and that's going to be equal to Vn. So this gives us our second order differential equation that's going to describe the mathematical behavior of the system. Alright, so we've derived the second order solution, the second order differential equation using the node voltage method. Now we'll find that it can be a lot easier to derive this equation using the mesh current method, and we'll look at that in the next video.